In the last video, we saw how entropy of the system has to do with the amount of arrangements that that system has. In this video, I'm going to be covering entropy of the surroundings. We can denote entropy of the surroundings with delta S, surroundings. Delta S of the surroundings does not have to do with the amount of arrangements in our system. Delta S of the surroundings has to do with the heat flow for a given reaction. We can actually relate delta S of the surroundings to our delta H of surroundings. Remember, delta H is a measure of enthalpy for a given reaction. So if we know the delta H of the surroundings, or the transfer of heat from the surroundings to the system for a given reaction, we can know a little bit more about the delta S of surroundings. So if we have a situation where we want to run a reaction where a solid is being converted to a gas, we can say that this reaction is taking place inside our system, and everything on the outside of the system can be considered the surroundings. So what is going on when we want to convert a solid to a gas? For delta S of the surroundings, we need to keep in mind intermolecular forces. So a solid has a high number of IMFs. A gas has no IMFs. So remember, as we move from a solid to a liquid to a gas, we are breaking IMFs. So in order to convert a solid to a gas, we need to break IMFs. So in order to break IMFs, we need to put heat energy into the system in order to run this reaction. Well, where are we going to get this heat energy? From the surroundings. So what we can say is that heat energy is going to leave the surroundings to come in to the system to break these IMFs. So what we can say is that the delta H of the surroundings is negative, meaning the heat flow is going from the surroundings to the system, so the surroundings lost energy. And remember, we can relate delta H of the surroundings to the delta S of the surroundings. So in the same light, we know that the delta S of surroundings is less than 0, because we, again, lost heat energy from the surroundings in order to put it into the system to run this reaction. Well, what happens if instead of a solid to a gas, we have a gas converting to a solid? Well, we know a gas has no IMFs and a solid has a lot of IMFs. So in order to run this reaction, we need to form IMFs. We can think of this as our system and this as our surroundings. Now remember, when we break IMFs, we need to put in energy to do that. Forming intermolecular forces actually releases heat energy. So heat energy will be released from the system to the surroundings. That means the delta H, or the enthalpy which measures the heat transfer in a reaction, is going to be positive for the surroundings, meaning the surroundings gained energy from the release of that system when we form those intermolecular forces. And remember, we can relate whatever sign for delta H surroundings to delta S of the surroundings. So delta S of the surroundings is going to be positive. So entropy of the system talks about arrangements. Entropy of the surroundings talks about heat flow, which we can relate to delta H of the surroundings, which measures the enthalpy or the transfer of heat to and from the system. Now, it is really important that we know intermolecular forces come into play when we are talking about entropy of the surroundings. If we break IMFs, in this case, to go from a solid to a gas, we need to put in heat energy. Where is that energy going to come from? The surroundings. We know that the delta H of the surroundings is going to be negative because we lost energy. Therefore, delta S of the surroundings is also going to be negative. In the case that we need to form intermolecular forces, we know that this releases energy from the system to the surroundings. So the delta H of the surroundings and the delta S of the surroundings is positive. So it is really important to know the difference between entropy of the system and entropy of the surroundings.